Here's example 2 with graphing a more complicated type of sine or cosine function. So again, it's a sinusoidal function, so we talked about that in the previous video. Sinusoidal function just means something like this, or maybe something with a phase shift. So we briefly talked about phase shift in an earlier video. We won't do examples with the graphing with it just yet. That'll be coming up in a separate video a little bit later on. But anyway, for now, let's go ahead and go through this example here. So again, just like with example 1, just like with that one, we could do the pre-calculus type of transformations, but it's a little more complicated that way because here with the sine function, it has nice periodic properties that we could use. Okay, and we're going to use those and follow these steps here, just like we did in example 1 with our cosine function example that we did there. Okay, so let's go ahead and go through the steps. So step 1, find the period t. Okay, so remember t is 2 pi divided by the absolute value of omega. Okay. And what's omega? So omega is the number being multiplied by the x here. So a sine omega x plus b, or a cosine omega x plus b. So let's zoom in a little bit here. Okay. So omega in our case is positive pi over 3, so that's good, kind of. Okay, so then 2 pi over omega is going to be, or 2 pi over the absolute value of omega is 2 pi over absolute value of pi over 3, but pi over 3 is already positive, so absolute value doesn't do anything. So we just have this. Okay, so then what happens? 2 pi divided by the quantity pi over 3 means 2 pi times 3 over pi. Okay, so we flip, multiply that, multiply by the reciprocal, the pi's cancel, that's great. We end up with 2 times 3, which is 6. Okay, so that's our period t equals 6. Okay, so that's it for step 1. So we'll put a big old fluffy cloud around that. So t equals 6, so that's it for step 1, find the period t. Now step 2, divide this interval 0 to t into 4 subintervals of equal length. This will make 5 x values. So again, this step sounds kind of complicated, but it's really not that bad. All we do is set up a little interval here. So let's maybe zoom out just a bit. So we set up an interval here from 0 to 6. Okay, and we divide it into 4 subintervals. How do we do that? Well, first we divide it in half. Now if we divide it in half, what number, so that's supposed to be half, but what number is halfway in between 0 and 6? Well, it's 3, right? That's not too hard to see. So let's maybe label these in a different color. So 0 and 6. Halfway in between is 3. Yeah, zeros, these are nice numbers to work with. So if you don't have nice numbers, remember just add up these two endpoints, divide by 2. So 0 plus 6 is 6, divide by 2 is 3. Okay. Now we divide each of these guys in half, and that'll be it for step 2. Okay, so divide this one in half. So what's that going to be? Well, 0 plus 3 is 3, divide that by 2, you get 3 halves. Which, yeah, is the same thing as 1.5, but let's leave it as a fraction. Okay, and because if we leave it as a fraction, it's going to be easier in step 3. Now the last thing to do here is divide this interval into 2. Okay, then what's this? Well, so these numbers aren't quite as nice, but 3 and 6, what's halfway in between them? Well, 3 plus 6 is 9. 9 divided by 2 is 9 halves. Okay, so not really the nicest number we could hope for, but not really too bad either. So that's 9 halves. Okay. Okay, so that's it for step 2. Divide the interval 0 to t into 4 subintervals of equal length. This will make 5 x values. So now we have our 5 x values. Now for step 3, find the y value at each of these x values. So what we do is just take each of these x values that we just found and plug them back into the original function. Okay, so let's go ahead and do that. So this is usually the most labor-intensive part because we're just plugging a bunch of stuff into the function. And you know, not much else is happening here, but it is kind of maybe the most tedious usually. But there is that pattern that forms that we talked about in the last video. That's going to happen here again, but I'll still go through all the details just to be thorough. But anyway, if x is 0, okay, so that's our first value, x equals 0, what's going to happen? Then we get y equals 2 times the sine of pi over 3 times 0 minus 1. Okay. So this becomes 2 times the sine of 0 and then minus 1. Now let's zoom in a little bit here. Sine of 0 is 0, so this is 2 times 0, which is 0. So that's 0 minus 1, which is negative 1. Okay, so when x is 0, y equals negative 1. Okay. Now what's next? 3 halves. Ugh. X equals 3 halves. Not really the nicest number we could hope for, but hey, this is actually not going to be that bad. What's going to happen? Well, what we get is y equals 2 times the sine of pi over 3 times x, which is 3 halves. Let's try that again. Times 3 halves, and then a minus 1 is still floating around outside, so we still have that minus 1 to worry about. And then this is 2 times the sine of what's happening inside. Pi over 3 times 3 over 2, so the 3's cancel. Okay, so we're just left with pi over 2, which is marvelous. Truly, truly marvelous. And then minus 1 is still out there. Then what's this? Sine of pi over 2 is 1. 2 times 1 is 2. So this is 2 minus 1, which is 1. Okay. What's next? 3 was the next x value. Oops. So x equals 3. So then we get y equals 2 times the sine of pi over 3 times 3. And then minus 1 is still floating around up there, so the minus 1. And then this simplifies to 2 times the sine of pi over 3 times 3. 3's cancel, and we get just pi, which is also marvelous, and then minus 1. So the sine of pi is 0. 2 times 0 is 0. 0 minus 1 is negative 1. Okay, so when x is 3, y is negative 1. What's next? X equals 9 halves is next. Ugh to that one too. X equals 9 halves. But actually, it's just like with 3 halves, it's not going to be that bad. So x equals 9 halves, what do we got? We got y equals 2 times the sine of pi over 3 times 9 halves, and then minus 1 still. Okay, so we're just plugging all the x values into this function here. Okay, that's the function that we were given at the beginning. So we're just plugging x values into there. And then what happens? 2 times the sine of what? Pi over 3 times 9 over 2, how does that simplify? So pi over 3 times 9 over 2, well 3 goes into 9 3 times, so this just becomes pi times 3 over 2, or in other words 3 pi over 2. Okay. So this is 2 times the sine of 3 pi over 2. And then we still have a minus 1 out there. So sine of 3 pi over 2 is negative 1. So this is 2 times negative 1. 2 times negative 1 is negative 2. And we still have a minus 1 here. So then we end up with negative 3. Okay. So let's get this out of the way to make some room. Now when x equals 6, two things. First of all, we don't even have to go through the calculation. Why not? Because we know the period is 6, and we already know that when x is 0, y is negative 1. So if we go 6 units to the right from x equals 0, then we're going to be at x equals 6. So remember, the periodic property says that if we go one length of the period, 6 units to the right, we're going to have the same y coordinate. So when x equals 6, y better be negative 1, okay? And it is, of course, because of the periodic property. But I'm going to write out these anyway because I want to point out that pattern again that we talked about in the last video. So y equals 2 sine pi over 3 times 6 minus 1, which simplifies to 2 times the sine. So pi over 3 times 6, pi over 3 times 6 simplifies to 2 pi, and then minus 1. So sine of 2 pi is 0. 2 times 0 is 0. So we have 0 minus 1, which is negative 1, which is what we expected from this up here. Okay. Okay, so that's it for step 3. Find the y value at each of these x values. So now again, I want to point out that pattern. Notice when we plugged in the first x value, inside of the sine simplified to 0. Plugged in the second x value, inside of the sine we got pi over 2. Plugged in the third x value, Inside the sine, we got pi. Plugged in the fourth x value. Inside the sine, we got 3 pi over 2. Plugged in the fifth x value, which again, we didn't have to do because of the periodic properties, but if we do that, then inside of the sine, we get 2 pi. So notice 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So that's the exact same pattern that showed up in example 1 in the previous video. And again, that will always happen as long as you follow these steps, as long as you use this interval 0 to t. Okay, so again, you could use any interval you want really, but 0 to t is the easiest to use for sure if you don't have any phase shifts. If you do have a phase shift, it's a little bit different. We'll talk about that in a separate video. But if there's no phase shift, meaning no horizontal shift, then just use 0 to t. And if you use 0 to t, then you'll always have this pattern show up. Okay, so 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's always going to happen. Okay, and again, I wouldn't recommend using that to evaluate, but it's a good way to check yourself. So if you end up with something more complicated in here, then that should tell you that maybe something went wrong, because you really should end up with 0, pi over 2, pi, 3 pi over 2, and 2 pi. But again, you don't even have to plug in this last value, because you could just use the periodic properties. When x is 0 and when x is 6, you'll get the same y value, in this case -1. So if you do it at x equals 0, we don't have to do it at x equals 6, but again, I just wanted to do it to show to point out this pattern here. Okay, so that's it for step 3. Step 4, plot the points and smoothly connect, extend the graph as needed. Okay, so now let's identify what the points are. When x is 0, y is -1. So this is 0, comma, -1. When x is 3 halves, y is +1. So that's 3 halves, comma, 1. When x is 3, y is -1. So that's 3, comma, -1. Okay. When x is 9 halves, y is -3. So this is 9 halves, comma, -3. Okay, and when x is 6, this y coordinate is -1. So 6, comma, -1. Okay, so now we have 1, 2, 3, 4, 5 points to plot, so let's go ahead and plot those. So we'll grab some of our graph paper here. So if you want to follow along with graph paper, but if you don't have any, go ahead and check the video description, and you can open up a PDF file. Click on that link to open up the PDF file and download some graph paper that you can print out. So first we want to set up our x and y axes. I'll probably make these way bigger than I need to, but why not? I'm just going to put them across the whole page here. X-axis, y-axis. Okay, so now what are we plotting? We're plotting 0, -1, 3 halves, comma, 1, 3, comma, -1, 9 halves, comma, -3, and 6, comma, -1. Ugh. So we got some fractions here. So since we have fractions, let's zoom in a bit. What I'm going to do is make each grid mark 1/2 of a unit. Okay, so 0, comma, -1 is going to be here. Okay, because each grid mark is 1/2 of a unit. So that's the scale I'm setting up. So 0, comma, -1 is here, so I'll label that here. What's next? 3 halves, comma, 1 is the next point. So 3 halves is 1.5. So 1.5, comma, 1. So this is 0.5, 1, 1.5, or we could say 1/2, 2 halves, 3 halves, and then up 1. So 3 halves, comma, 1. Okay, oops, wrong point. 3 halves, comma, 1. Okay, so if each grid unit is 1/2, then this is 1/2, 2 halves, 3 halves, and then 1/2, 1. So that puts us up here. So this is 3 halves, comma, 1. Okay, what's next? 3, comma, -1 is next. 3, comma, -1 is next. So 1, 2, 3, and then -1. Now if you're following along, you don't have to use the same scale that I'm using, of course. It's just easier for me, personally, to have everything be on a grid mark, on a grid corner of the grid box here. But you know, you don't really have to do that, of course. So this is a 3, comma, -1. As long as you keep your scale consistent and if it makes sense and everything, that's all that really matters. Now what was next? 9 halves, comma, -3. Okay, so Now we don't really have to count it out like this, but why not? 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7, 8, 9 halves. Okay, so 9 halves puts us right here, and then what was that? 9 halves comma negative 3. So negative 1, negative 2, negative 3. Okay, so 9 halves comma negative 3 is down here. And then, so let's label that. And then what? And then last was 6 comma negative 1. So that's going to be, so 9 halves was over here. 9 halves, 10 halves, 11 halves, 12 halves, which is really 6. Okay, so this is 6 comma negative 1. Okay, so that's one complete cycle. So now we just want to smoothly connect. So remember, plot the points and smoothly connect and extend the graph as needed. So just like with the cosine graph, we want to be very careful. It looks like we could just connect with straight lines, and we can, but we absolutely do not ever want to do that because we're graphing trig functions, sine and cosine. So we want to make sure that we give them that curvy sine type shape. Okay, so give them that nice curvy shape here. Okay, and then extend as we need. So there's not a whole lot of room over here, so we'll just extend it this way, just a little bit. And then let's extend one more cycle over to the left. So remember the period is t equals 6. Okay, so that's our period. So that means if we go 6 units to the right or to the left, we're going to be at the same y coordinate. So like here, 0 comma negative 1 goes 6 units to the right. Here's 6 comma negative 1. What if we go 6 units to the left? Well, that's going to be negative 1, 2, 3, 4, 5, 6. 6 comma negative 1 is over here. Okay, so that's what we got going on here. So that's 6 comma negative 1. All right. What about 3 halves comma 1? So if we go 6 units to the left, here's 1 unit, 2 units, 3 units, 4 units, 5 units, and 6 units. So that's going to be this point here. What is that point? I'm not sure. So 3 halves minus 6 is 3 halves minus, so multiply by 2 over 2, that's going to be 12 halves. So that's negative 9 over 2. Okay. 3 halves minus 12 halves is negative 9 halves. So this is negative 9 halves, comma what? Comma the same y coordinate as this point here, 1. Okay. What about over here? 3 comma negative 1. If we go 6 units to the left, we're going to be at negative 3, 2, 3, comma negative 1. Okay, so that's negative 3, negative 1. How about here? 9 halves, comma negative 3. If we go 6 units to the left, 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units. That's actually going to be negative 3 halves, comma negative 3. Okay, so same y coordinate as this guy over here because they're 6 units apart. So remember the period is 6. So since the period is 6, if we go 6 units to the right or to the left, we'll have the same y coordinate. So that's why this is also the same y coordinate. So then we can extend this graph this way. It's easier for me to go left to right. It's easier to get that curvy shape for me anyway. Okay, so that's pretty much it. Now we do want to make sure to extend this part over here because we do want to emphasize that we do want to make sure that we capture the fact that this does go infinitely far this way too. So zoom out just a bit. Okay, so here is the graph of our function y equals 2 sine of pi over 3x and then minus 1 out here like that. So when we went through the steps outlined here, okay, when we went through these steps, we ended up with this right here, this right here. Okay, so from 0 to 6, that's one complete period, and then we extended it a little tiny bit to the right here. We've got to make sure we put that arrow over there to show that it does go infinitely far this way. So this pattern does keep repeating. So if we go 6 to 12, it'll look exactly like this. So here's 0 to 6, 6 to 12, 12 to 18, and so on. It's going to look exactly like this. But then we did extend one complete cycle to the left. So here's, sorry, that should be negative 6. Negative 6 comma negative 1. So if we extend far to the left, negative 6 to 0, okay, it's the exact same thing as if we go 0 to 6. So 0 to 6 looks like this, negative 6 to 0 looks exactly the same thing, negative 12 to negative 6 would look exactly the same way, and so on. Okay, so that's example 2 with graphing a more complicated type of trig function.